Hello class. Today we are going to be looking at the situation where we might see problems where we see both the things that we were looking at when we were doing kinematics and some of the stuff that we were looking at when we were doing dynamics or forces. And so the idea behind today's lesson is that nothing that we cover in any physics class gets stopped or forgotten. Is physics constantly builds and grows on itself. So everything that we've been doing is still applicable and will be applicable for all the future stuff as well. So let's just consider when we were solving for kinematics problems, what variables did we end up looking for? We ended up looking for uh, initial velocity, final velocity, acceleration, displacements, and time. And so those were the variables that we tended to use for kinematics problems. When we were dealing with forces problems, we ended up wanting, obviously, force, masses, accelerations, coefficients for the friction, spring constants, distances stretched. But that basically covers it. And if we take a look, there's clearly a bunch of differences, but there is a very noticeable similarity. Acceleration is the shared variable. So if we ever have information about kinematics, and if we ever have information about dynamics, and we would need to find out, can I get from one to the other, acceleration is our connection there. Right? Acceleration is the way that these two things connect. So our connecting variable here is acceleration. Now let's actually go over a problem. Let's see what we're talking about here. Uh, we have a mountain climber that's falling next to a cliff, and the climber slams her pick into the wall to slow down her descent. And the pick exerts 730 newtons of force to slow the climber. How fast was the climber falling if she slid 33 meters down the cliff before coming to a stop? Oof, there's a lot going on here. So let's just see what can I diagram this to help me out. So we first have a person who is falling. Oh no, they're falling, and they're falling some velocity, which is how fast was the climber falling at first. So this is what we're trying to find out. How fast were they falling? What they do is they slam a climbing pick into the wall, and this provides an upward force on the person, because if they're falling, an upward force would be what slows them down. So I'm calling that FP for F pick, and that's 730 newtons. And that will slow them down eventually until they come to a stop, so that's VF, and we know that the distance from here down to here was 33 meters. Now this diagram is pretty good, but my forces are actually incomplete. The pick force isn't the only force acting on this mountain climber. The mountain climber also has gravity acting on them, don't they? Because that's kind of how this works. So I've got a lot of information here. I have some velocities, I have some displacements, I have some forces. How am I supposed to solve this problem when it looks like I have information both from forces and from kinematics? Well, you just kind of do them both a little bit. You kind of ask yourself, where do I want to start? Should I start by thinking about my forces, since I have my free body diagram, or should I think by starting with my kinematics? Generally, if you're ever completely uncertain and you're like, I don't know where to start, is I start with the question itself. What was the initial velocity? That was the question itself. And when I'm looking for initial velocities, that's a kinematics idea. So I'm going to do my kinematics side first. Kinematics. Let's start like I usually do. I list out my variables. And this will help me determine if I need to use, which formula I need to use. So initial velocity is my unknown, give that a question mark. My final velocity, this person's sliding till they hit a stop, so I'm going to give that a 0. 0 meters per second. The displacement they have is 33 meters per second, is 33 meters. And I noticed that they went up and they went down, so this is 33 meters in the downward direction. Now, do I know the acceleration? It's not 9.8, because that would only be the case if they're free falling, but they're not because of this pick. And do I know the time that they took? No, that wasn't given. So I'm left with not enough information. And so I need to know some more information, but I notice I have some forces, and what is my connecting piece between force and between forces and kinematics? It's acceleration. So if I can find my acceleration, I know that's my connecting piece. So maybe over here, I'm going to pay attention to forces. Well, what do I do with forces? I've got a little free body diagram, force up and force down, and if I have a little free body diagram, I can make a net force equation. Now, if I'm doing my net force equation, I can put in what it is. Maybe I'm going to do up minus down, perhaps. Maybe that's what I'll do. So my pick force here is going to be subtracted by my gravity force. And my net force is m times a, the mass being 58. The acceleration is what we're trying to find out, because if I find this acceleration, then we can use that over here for kinematics. The pick is 730, and we're going to subtract the force of gravity. I'm going to bring out my gravity. It was mass, 58 kilograms, multiplied by 9.8. So that's 568.4 newtons. 568.4 newtons. I can do that. I can do that subtraction, and then I will divide both sides, the entirety here, by 58. So do the subtraction first, then divide by 58, and this will get us the acceleration. So 730 minus 568.4. I hit my equals button first, and then I'm going to divide that by 58. And it looks like 2.78. I'm going to round that to 2.8. So let's see. I'm going to round this to 2.8 meters per second squared. Now, something that we have to keep careful of, because this is 2.8 meters per second squared. That's all good, right? This goes around into there. That's good. But something I need to be careful of is I need to pay attention to direction. Look at your net force. I put my pick force first, which means I said pick force direction is positive, gravity force is negative, and so this became positive. Well, what direction is my pick force? It's up. So this is 2.8 meters per second squared upward. So this is upward. Now I have enough information. VI, VF, A, and D are the variables that I'll be dealing with, and the formula that connects with it, I can use my formula sheet and find that would use VF squared is equal to VI squared plus 2 times A times D. Or if I rearrange, that 2 times A times D comes to the other side as a subtraction, meaning VI squared is equal to VF squared minus 2 times A times D. And then I will take the square root of both sides to get VI all alone. Now, one thing to note is you have to watch out for these signs. Notice how the acceleration was up, but the displacement is down. So I need to define my directions. In forces, I already defined up as positive, and I already defined down as negative. Maybe I'll just stick with that. I'll call up positive, and I'll call down negative. So this means this is positive, that's negative. Let's put this in and see what we get. VI is equal to the square root of 0 squared, because that's VF, minus 2 times 2.8 times negative 33. That's actually going to be really reassuring, because that negative and that negative are going to cancel, meaning we have a positive number that we're taking the square root of. Let's grab our calculators and do that. 0 squared is 0. 2 times 2.8 times 33, the two negatives cancel out. That's 184.8. Take the square root. It's 13.6. 13.6 meters per second. Now there is something for us to watch out for. Remember, when we take the square root, you could always have the positive or the negative of this responses. So the question is, should I choose from this context, did this person originally start by falling up, or did they start by falling down? Hopefully you got that there, because they were falling down, and down we defined as negative, so I would say negative. Or I would write it in a sentence and I would say they started by falling 13.6 meters per second downward, right? So more right, downward. So that's how we do these problems. I make sure I understand the problem. As you can see, I started by diagramming it. And when I notice that I have kinematics relations, or variables, or velocities particularly are a giveaway, and if I notice I have force variables, I will kind of separate them, and I will start solving one, and if I get stuck, I jump to the other one, and I find the acceleration, because that acceleration is that connecting piece. Let's give the next problem a try and see where that takes us. So here we go. We have a potato is launched horizontally from a potato cannon. It starts from rest when it experiences a thrust force and speeds up to 25 meters per second by the time it leaves the barrel. There's 35 newtons of friction between the potato and the barrel, which is 3 meters long. What is the thrust force provided by the potato cannon? Well, if I was to draw this out, here's my horizontal potato cannon. Here is my potato as it starts out with. This very start of my potato cannon is at rest, 0 meters per second. And then it's shoved along, it's moved with some friction resisting the motion, force friction there. And there's some thrusting force, F thrusting force, that's pushing it forward, so that when it leaves the barrel at the very end here, it should be going a velocity of 25 meters per second. And this occurs over a whole 3 meter long distance. So again, if we're wondering, I'm not sure where to start with looking at the question. The question is, what is the thrust force? So it's asking us for the thrust force. We should think of force. All right, I'm going to go ahead and start my side here, force. How do I approach my force problems? Well, I have my little diagram with my forces here. I just need a net force equation. F net is equal to, well, the thrust force makes it move, and the friction resists it, so it's going to be F thrust minus F friction. The net force is mass times A, so that's good. 0.50 times, I don't have the acceleration. Nuts, I don't have the acceleration. Force thrust minus friction is given, is 35. I need to find that acceleration. If I find that acceleration, we can solve this problem. So since we're stuck on our force end now, we got our information, we got going, but we're stuck now, we're going to move over to kinematics and see if we were able to find the acceleration in kinematics. Let's see, initial velocity 0 meters per second, final velocity 25 meters per second. The acceleration is what we hope to find. If we find that, then I'll solve our problem for us. Displacement was 3 meters. Time was, we don't know the time, do we? But there's actually enough information, VI, VF, A, and D. I actually am going to use the same formula as we did in our previous question. VF squared is equal to VI squared plus 2 times A times D. Solving for the displacement, this comes over as a subtraction. VF squared minus VI squared is equal to 2A times D. And then I can divide both sides by 2A. So D is equal to VF squared minus VI squared, all divided by 2A. That's going to be 25 squared minus 0 squared, so it's just 25 squared, all over 2 times. Sorry, everybody, we don't want to solve for D. We want to solve for A. Apologies. Let's just do a little fix for algebra. On the bright side, this isn't actually too much of a fix. 2 times A times D, we want to divide by 2 and D. There we go. So this is 2D there, and D happens to be 3. There we go. So sorry, everybody, I solved for the wrong variable. On the bright side, it was actually a pretty easy fix. We didn't need to fix too much. So A is equal to 25 squared, if I'm not mistaken, is 625. Let's just double check. 25 squared divided by 2 times 3. 2 times 3 is 6, so divide by 6. Oh, that's 104.16. I'll just call it 104. 104 meters per second squared. This acceleration we can now bring right in here, 104, and we could finish off our work. 0.5 times 104 is going to be 52, is equal to thrust force minus 35. That comes over as an addition. So 52 plus 35 is going to be 87 newtons. 87 newtons of thrust force to accelerate that potato from 0 to 25 meters per second inside the 3-meter cannon. I hope that this approach makes sense to you, is that we diagram to make sure we understand our situation fully, and we write out the things that we know, and if there's both forces and kinematics, like you'll see velocities and displacements, the connection between the two is acceleration. And so if you find that you get stuck on one end, just look at the other side. Can I find that acceleration? And then move it over. That's it. Please practice this. This idea of connecting our units together is something that we're going to be doing every time, because all of these things connect together. So good luck, everyone, and see you later.